So let's look at Euclidean geometry. Most of you would be aware that it's one of the first axiomatic. Okay, let me check this. There's axiomatic system of geometry. This means axiomatic means that we start with this few basic axioms and derive all possible theorems from those axioms. So this is how the Egyptians, mostly Euclid, formulated the geometry. It was close to about 2 to 3 centuries BC. Okay, and they started with these 5 axioms. Most of them are extremely obvious. So given 2 points, there's a straight line joining them. So this is, I have 2 points and I can always join by a straight line. Even though they didn't clarify what a point is or what a line is, they are supposed to be understood intuitively. And a straight line can be prolonged indefinitely. Again, obviously, that is, I can keep on extending it in both directions. And given a point and given a radius, we can construct a circle around that one. The circle means that it is a set of points which are at a constant distance from the center C. Okay. And all right angles are equal. Right angles is just an angle like this one. So all right angles are equal. And all these 4 axioms are really meaning almost obvious. But the 5th axiom is a sort of difficult to understand. So what they are saying is that suppose I have 2 straight lines and I have another line meeting those lines. And if the sum of these 2 angles is less than 2 right angles, and these 2 lines are supposed to meet on that side. If I extend them sufficiently further, they should be meeting at that side. Okay, so this is what is usually called the parallel postulate.
Sir, can this also be called as Playfair's axiom?
Pardon?
Sir, is this also called as Playfair's axiom?
Playfair's axiom, I am not sure. This is usually called a parallel postulate. And this is equivalent to something like the most fundamental theorem which you study in geometry, where the sum of the angles of a triangle ABC is equal to 180 degrees. In fact, these two are equivalent, meaning if you assume parallel postulate, you can derive that, and instead you can assume this as well, meaning sum of the angles of a triangle is equal to 180 degrees and so on. So of course, there are lots of research after Euclidean geometry. In fact, what actually is geometry is uh, has been the question for several mathematicians, and people also question what happens if the sum of the angles of a triangle. Are there situations in which sum of the angles of a triangle is less than 180 or more than 180 and so on? And what happens if we just replace this parallel postulate or this postulate, that is sum of the angles as 180, with any of these 2 things? For instance, if you take an ellipse, meaning okay, even if you take a circle, and then if I just look at these 3 triangles, this triangle, that is, I have this. Suppose if it is the Earth, let's for instance, this will be the equator. This is this point, and so on. Here, all the angles are 90 degrees. So in this spherical triangle, the sum of the angles is not 180; it is more than 180. On the other hand, if you take a surface like this, which is what's called a hyperboloid, and you can show that the sum of the angles will be less than 180 degrees. So there are geometries, different geometries other than Euclidean geometry, which could be derived by replacing this axiom. Okay. Anyway, we are not interested in that part of the story today. We are interested in something else. And right from the beginning, the Greeks were very much interested in constructions. That is, if you look at Euclid's book, he constructs lots of things. He constructs a regular triangle, that is the constructions. And again, these are some special constructions in the sense that they are not interested in constructing by measuring something and so on. So they wanted constructions only using a straight edge. A straight edge, which means not your scale, which has markings and so on, just a plain straight edge. I will show you a picture, and a compass. So what are the figures that we can construct using only a straight edge and the compass has been sort of investigated by Euclidean geometry in many occasions. For instance, suppose I have to construct, let's call something like a regular polygon. Suppose I have a regular polygon means the polygon with, let us say, n sides, in which all sides are equal, and all angles are also equal. All angles are also equal. So if I call this as a regular polygon, a regular triangle is basically equal to triangle, and then I can always construct it using straight edge and compass. Okay, by straight edge, what we mean is this. That is just straight, meaning something which we can draw a line with. The compass is this one. I don't know why. I hope many of you would have seen compass and dividers and so on, right? These days, do you still, in geometry class, do you still draw pictures? Sorry, construct things using that one? I don't know. We used to do it when I was a child, when I studied in 10th and 11th standard. There are lots of constructions which we used to do. And
Yes, sir, we did for angle bisector and all that. We need compass.
we do that. And at my time, there were close about 20 plus constructions. Now, a couple of weeks back, I saw the CBSE textbook for 10th standard and 9th standard. There are hardly any, about two, three, that's all, nothing more than that. And it was really unfortunate. And most of the constructions are also very straightforward. For instance, given three sides of a triangle, draw the triangle, or given an angle, bisect the angle. Uh, Interesting problems like can you construct a triangle? Let us say, let me just give a construct a triangle given, let us say, its orthocenter, in center, and one of its vertices. Can we do that? Okay, so these are some of the very interesting problems which sometimes the answer may not exist at all. We cannot do that. Sometimes there may be more than one triangle with this property, like that. So that is what it is challenging. In fact, way back in 1989, one student from Bombay by name Arvind and myself wrote a book, meaning wrote a small book, which is called Triangles. Title is Triangles, Constructions and Inequalities. Constructions and Inequalities. In this book, what was investigated is that all constructions which are possible by giving 3 points of a triangle, any 3 points, like one orthocenter, one excenter, one center, things like that. And this construction part was written by Arvind, who was in the 10th standard at that time, or he was in the 9th standard at that time. Okay, and the inequalities part I wrote. But the thing is, these kind of problems are not at all investigated these days in schools, which is really surprising. Okay, yes, Manu.
Sir, this triangles, then this combinatorics, and one more book you wrote, like recursion sequences. Are all these published under AMTI?
Yeah, one of the now see, except the combinatorics is not published under AMTA. The others are published under.
Sir, now in the AMTI book list, this is also there.
Yeah, it's
Com-
also now it is also there, but commodities is not published by AMTA. It's published by somebody else. Okay, let's come back to this one. So regular polygon of n sides. Uh, See, we have this. One second. We have this regular triangle. Is what triangle is equilateral triangle. Definitely can construct given a side, let a side length. What you do is that you just draw an arc like this with this as a center, and take this intersection point, draw the same arc, the same radius, and then if you just join these two, you get an equal triangle. Okay. Note that I have not used any measurement at all here. So only except that the side length is given. Side length is given, or
Any radius.
any radius. Okay, any radius. No. If the side length is 1, the radius has to be 1. Here also the radius has to be 1. So then I'll get triangle of this one of equal triangle side 1. Similarly, if you want to construct a square of side length 1, let us say, and what I do is that I just do this one, and I can just draw a semicircle with this as a center, any semicircle, and then bisect this one. Then I can draw this perpendicular by perpendicular, isn't it? So you already know that how to perpendicularly bisect a segment. So perpendicular do that. And then mark this one length, and then again perpendicularly bisect, again bisect like this. I get a triangle. I get a square. So I can draw a equilateral triangle. I can draw a square. Again, I have noted that I have not used anything other than the straight edge and the compass. Most of you would have also seen the construction of a hexagon. So you take a point, and then suppose this is the radius, mark off chords of length equal to the radius like this, then you will get an hexagon, a regular hexagon, of course. Okay. And have any of you seen how to construct a regular pentagon? Again, see, let us reiterate the regular, anywhere, whenever I say construct, whenever we say construct in these two, in today's and tomorrow lectures, it essentially means that only using straight edge and compass. Okay, so we can't say that, like, see, the regular pentagon, the interior angle is 108 degrees, that you already know, isn't it? Because if n is the number of sides of the polygon, it is n minus 2 by n into pi, which is equal to 3 by 5 into 180, which will become 108 degrees. So what we can say is that I can just draw this straight line and then use the protractor. You have something like that, isn't it? And then mark off 108 degrees and then do. No, that is not allowed because it uses something other than straight edge compass. Okay. So can you construct? Have you seen a construction of pentagon using using only straight edge compass?
Sir, I've seen it in a video, but it was a bit complicated, so I don't entirely remember.
Oh, I remember. Okay, let me ask a simpler question. All of you would have been taught how to bisect an angle, right? That means
Yes.
what you do is that you just draw this arc and then draw an arc like this, same distance, draw an arc like this, and then this will be bisecting this one, correct? Now, have you been taught how to trisect an angle?
I think it was proved to be impossible.
Proved to be impossible, but you have been told that it is impossible?
Sir, we have not learned anything.
Yes, sir, it is impossible.
It is?
Impossible because if you are given a particular angle, then if you divide it by 3, you will not get any what we can ending value. We will get always a recurring value.
No.
Sir,
Suppose I
we
say,
will not.
no. See, it's not about recurring value. Suppose I give you 60 degrees. Can you trisect this? Trisect this mean again, say whenever I said, I already say, let me not repeat again and again. Thing is, construct or trisect or whatever we talk about a construction in this class, it will be always using straight edge and compass, nothing else. That is what Euclid was interested in. That's what people are interested in also. So trisect an angle 60 degrees. So here, if I just divide this by 30, there is no recurring thing at all. It is just 20 degrees. So can we trisect the 60 degrees? And let me see.
So if you know how to draw 20 degrees, then yes.
Yeah, but do you know how to draw 20 degrees?
Sir, we can't.
Compass. Now let me show you a trisection of a right angle. 1 second. Yeah. Using again just a board ruler and compass.
Sir, for trisection of a right angle, we can just construct a equilateral triangle and equilateral angle, then 60-degree angle and bisect it.
Yeah, that is one way. Let me give you another way of trisecting a right angle. So just take first of all draw this right angle, okay, and then take any radius and draw a circle like this, and then mark the intersection point like this one, and again the same radius draw another circle and mark that intersection point, and draw with that as a center the same radius, draw another circle, let this be the intersection point again, and then do the same. Of course we don't need that at all, but anyway, so if I just draw this one more circle and then draw this one, then what I get is that if I just do these two things, that will be the trisection. And if you have any doubt, I can also measure it and show it to you. That is
Sir, it will work only with 90 degrees, no sir?
It works with 90 degrees. Okay, it works with
But
90
it won't
degrees.
work with other angles.
Huh?
But it won't work with other angles.
That is correct. It won't work with other angles, I know.
Then what's the point?
Huh?
We already know how to construct 60 and 30, so
Yeah, this
nothing
works with
is.
this one. So the point is, can any angle be trisected? Okay, that is the question which they are interested in. In fact, they were interested in several questions like this one. That is it possible to double a cube? Double a cube means, suppose given a cube of volume 1, okay, and can you construct another cube of volume 2? That is the
So
side.
volume 2, right? Not
Double
side
volume.
by 2.
The volume 2 means this has to be cube root of 2. So the question is basically asking, can you construct cube root of 2, like that's what, using ruler and compass alone.
So how will you construct on paper, sir? That's 2D, right?
No, construct in this sense, that is what we want is a construct in the sense that given this one, that's what I said, it's same as constructing cube root of 2 as a length, that's all. See, from 1 can I find out, see, from 1 I can find what is half, I can find 1 by 3, I can find 1 by 100 also, because I can just draw this line, divide this into 100 parts here, and then join this one, and then keep on drawing parallels. This would have divided by 1 by 100, right? That could be done. So dividing a line any number of times is fine, but can you construct cube root of 2 from a given length 1? That was the question which you
Yes,
were talking.
sir. Yes, sir.
Can? How?
Yeah. So we will draw first a line segment. Then we will take 1 unit distance on it, and from a particular point, we will construct a perpendicular which will also be of 1 unit distance. So if you join the starting point and the top point of perpendicular bisector, so the hypotenuse will be √2. Then we will take that distance in a compass, and we can construct
Not, it is
our
cube root of,
cube
it is
root.
cube root of 2, not root 2.
Sir, I have a question regarding the previous construction.
Mm-hmm.
Sir, I do not understand why is it working? Why is it trisecting the angle?
Okay, that's for you to find out.
Okay, sir. Sure.
I just drew the circles, that's all. So that's for you to find out why it constructs 30 degrees. It's a simple geometric problem. You can.
So does straight edge have measurements, or is it only a?
No, that's what I said. It's not a ruler. A ruler will have measurements, and a straight edge doesn't have any measurements at all. Okay, that's the difference. The difference is that the straight edge does not have any measurements on it at all. That's where the key difference is. Okay, so I can't measure 1.72. I can't do that in this. Unless I can construct 1.72 using compass and this straight line. Okay. Okay, so they were asking these 4 questions. That is it possible to trisect any angle? Are there regular polygons which are constructible? So we already saw the triangle and square. And let me show you a pentagon construction. Okay. Again, that it does construct a pentagon, regular pentagon is left as an exercise. See, what you do is that we just draw a circle of radius 1, let us say. Okay. Then draw a diameter. That's always I can do, right? I have one point here, the center, and then I can take any point on that circle and then draw this line, and that will be a diameter. Once I draw the diameter, I will draw a perpendicular diameter. That I already know how to do that. Okay. In fact, that's not required. In fact. Okay. And then draw this other end point. Okay. And mark this other end point and bisect this part of the diameter, that is this radius. You have bisect at this one, and then take this as the radius and this as the center and draw a circle. It will intersect at 2 points, this point and this point, correct? The diameter will be intersected to these 2 points. Then mark those 2 points, and with this as a center and this radius as the radius, okay, draw another circle and let it intersect at this point and this point. And similarly, With the other end point, draw another circle. Again, let it intersect at these 2 points. Now join those 5 points. That will be a pentagon. It's a regular pentagon. Okay. So all the sides will be equal. And if you want, I can measure it for you if you want. 1 second, let me show you the length. The length of this is 4 point whatever. This also 4.7. This also is 4.7, 4.7, and 4.7. So definitely we got a regular pentagon, or the sides are equal. And I can also measure the angle if you want. So let me measure the angle as well. This, and this is definitely 108 degrees. Correct? So we have got a regular pentagon like this one. So this is a construction for regular pentagon. But no wonder it is not being taught to you, right? Okay. But anyway, so you can have fun like this in any case. Yeah, there was somebody who rose, Smithali.
Sir, how do you construct the third circle, which will be the center?
Which one?
The third circle the fourth circle you drew, the last one. Yeah, after this.
After this, one second.
Which is the center for?
This is for the next circle. This is the center and this is the radius.
Yeah.
And the other circle is at the other end point. This end point,
Oh,
same radius. Same
yes.
radius.
Okay.
This circle intersected at 2 points, and then there are these 2 things are these 2 circles are drawn, and the end and the intersection points of the main circle there. That is the red circle which you drew in the beginning. Those will be the vertices along with this end point. That will be the pentagon's vertices.
Yes, sir.
Yes,
Sir, sir, but how will we construct a pentagon for a given side? If you are given a side,
given side is okay. That's a good question in any case. Given side is what? It was not that bad.
I think, sir, if we find the value of the side of the pentagon in terms of the initial circle we draw, then maybe we can do something.
We don't have to do that. In fact, there is other way to do that. But in any case, okay, okay, let me show you another way of doing that one. Okay. Now, you can see sine of 18 is root 5 minus 1 by 4. Okay. Sine of 18 is root 5 minus 1 by 4. So you can easily construct root 5 because I can construct a right angle triangle. I can just have 2.2 here and 1 here, and this will be root 5. And then I can just measure off 1 using compass, like this will be root 5 minus 1. And I can divide this into 4 parts. Okay, so I have constructed root 5 minus 1 by 4. So I just take this one, and then what I do is that I just draw a perpendicular. Okay, and then take this as the root 5 minus this distance as root 5 minus 1 by 4, and take this as the center, and then take a radius 1 and then cut off this way. Then I would have got this as the 108 degrees. Okay, but since I can, sorry, this is 18 degrees. Since I can construct 18 degrees, what I will do is that I just take a line like this, take a point like this, and then draw a perpendicular like this one, and then draw this one 18 degrees like this one. Once I do that, then I can mark off 1 distance here and 1 distance here. Then those 2 will be the vertices of 2 polygons, and draw this full circle and mark off the same distance with the other 2 points. Then I would get a pentagon with side 1. Okay, that's one way of constructing, given a length, and then do that one. Okay, so this way we can do a pentagon as well. But the other construction was interesting because it just used just circles and only circles and then intersection points and so on. Okay, right. So let's go for further. So since I can construct 3, 4, 5, 6, can also construct 6, 8, 10, 12, and let us say then what else I can construct? So 6, 12 I can construct, and okay, then what else I can construct? So 16 I can construct. Then I can construct 20, 24, and so on. All these things are possible because if I can construct an n gun, and in an n gun, suppose I have these are the n guns. If I bisect all these sides, those vertices along with the original vertices will form a polygon of regular polygon of 2n sides. So I can once I can construct n, I can construct 2n also, or I can construct 4n, or I can construct 8n. More generally, I can construct 2 power n, sorry, 2 power k into n sides. So all these things are possible, and we have 3, 4, 5, 6, and so on. All these things are really have been already done using regular compass and so on. Okay, right now, can we construct a polygon of? Can we construct regular polygon? Can we construct a regular polygon with 7 sides, or 9 sides, or 11, or 13, or 17, all of them? Or more generally, if I have a prime P, for which values of P I can construct regular polygon? Can I do it for all primes or only for certain particular primes and so on? Okay, right. So this was one of the questions which they were interested in. The other more important question was that is it possible to construct a square with area equal to that of a circle? Okay, that was another question which they were interested in. So this one, doubling the cube and then trisecting an angle and then constructing a regular polygon, and these things have been around for close to about 2000 years with nobody answering it conclusively. Okay, so till one great mathematician came along and then settled all these things in one go. So let's see who that is, and then we will look at what he did as well. Before we proceed, let us look at what are the things we can do with a straight edge and compass. So we can draw a circle, of course. We can bisect a line perpendicularly, that's possible. We can draw also a perpendicular to a line at a given point. Suppose I have a line at a point. First of all, I can just draw a circle and then take these 2 points and then perpendicularly bisect this segment. And that will give me a perpendicular at this point. Okay, so this is possible. And again, I can draw a line through a given point parallel to a line. Suppose I have a line like this. I have a point like this. First, I draw a perpendicular like this one. Then I can draw a perpendicular like this one. So these two will be parallel. Okay, right. So this is possible. And divide a segment into a number of parts. Since I can draw a line parallel, what I do is that I have been given a segment like this. I draw any line to one end point, then mark off equal distances, n equal distances here, and then join this end point and keep on drawing parallel at those points. If I do that, by similar property of the triangles, these also will be equal. So I have divided a segment into n equal parts for any n. That is also possible. And of course, bisect any angle we can do. And construct a regular polygon with n sides. This we already seen. One more thing we can do, that is, given a length a, I can construct root a also. So let's see how it is possible. So this is a simple similar triangle thing. What I do is that I just draw a segment. This is length 1, this is length a, and draw a semicircle on that. This is possible because I can just bisect this one by using ruler and compass, and then I can just draw this semicircle with this as center and this as the radius, and drop this perpendicular here at this one thing. Okay, then we claim that this length is root a. That's because if I join these two things, suppose I call this as a and b, and this as c and this as d. So this is 90 degrees. So if this is theta, this is 90 minus theta because this is 90 degrees. So this will be theta and this will be 90 minus theta. So the triangles ACD is similar to triangle BCD. So what is the side opposite to, suppose this side length is x, let us say CD is equal to x. If I put CD is equal to x, my x by x is a side opposite to 90 minus theta in this triangle. The same 90 minus theta, what is the opposite to the other triangle? It is 1. So x by 1 is equal to So again, the side opposite to theta in this triangle is A. Okay, A, and then the side opposite to theta in the other triangle is x again. So I get x square is equal to A. So my x is equal to root A. So I can construct root A. We can suppose I have length 2. One length is means I can construct 2. So I can construct root 2. I can construct 3 because I just mark a line, mark 1, 1, 1. I have constructed length 3. I can construct root 3. Okay. 1 second. Who are they?
Sir, can you please do this process again? I didn't understand.
Okay.
Sir, and one more question.
Mm-hmm. Yeah. Go ahead. Hello.
Sir, I have a doubt.
Ah.
So how can you do?
Sir, how did you get theta there? Like if that is theta, how did you get theta there?
No. Okay. So what? Okay. What I'm. Let me repeat it again. That's so that we can. What I do is I just draw a big line. In that I take one point. I mark 1 here, and from this I mark A. Both are given. Let us say, isn't it? Now I bisect. Suppose I call this as A and B. I bisect this segment at C, or say at D. Then draw the circle with D as center and DA as radius. I do that. Then from this point to this plane, I can draw a perpendicular. This I can do that, isn't it? No issue at all. Again, I have not used any length and all those, meaning anything other than straight edge and compass. Then let it meet at this point C. I join this one and join this one. Okay. Now we claim that the triangle ACD is similar to triangle BCD. Sorry, this is this is my. Let me. So this is D means this is B. Let us put the C. Triangle ACE is similar to triangle BCE. So D was the center anyway. Okay. How is that possible? So this is 90 degrees. We know that I have drawn a semicircle. So angle in a semicircle is 90 degrees. Correct? Angle in a semicircle is 90 degrees. Suppose if this angle measure is theta, I don't care what that measure is. Okay. And this measure will be what? This is theta. This is 90. So this angle must be 90 minus theta. This total angle is 90. So this angle, this part is 90 minus theta. So this must be theta. Again, this must be 90 minus theta. Because this is 90 degrees, right? So in this triangle ACD, I have theta, 90 minus theta. In triangle BCE also it is theta, 90 minus theta and 90 degrees. That's all. That means I have these two triangles are similar. When these two triangles are similar, let me look at what this is x. Suppose this length is x. I want to find what that x is. So x in this triangle is opposite to 90 minus theta. What is opposite to 90 minus theta in the other triangle? The other triangle it is 1. So x by 1. And in this case, the angle, the side opposite to theta is A. The side opposite to theta in this is x again. The smaller triangle is x. So A by x. So this is by just similar triangle property. That means I have x square must be equal to A. So this x length must be equal to root of A. So from A, I have constructed root A. So this will be root A.
Sir, but how did you get the length 1 without a ruler?
No, I said, see, there is a straight edge and there is a compass and there is a unit. That is also given. But it's not given on the straight edge. We are given 2 points on the plane and say it is 1 unit. That's all is given. I can replicate this anywhere by using compass. But I can't mark 2 points on the line. I can't mark, suppose I have this straight edge, I can't mark 2 points like this and then call that one. That's not what is intended at all. In fact, if we do this, okay, if I have marked ruler like this, then I can trisect any angle using this. That is possible. Okay, but anyway, we won't go into that. So it is not marked ruler. The angle is, the point is, we are given 1 unit. Otherwise, meaning length doesn't make sense at all, isn't it? If we are not given the unit at all. So the length doesn't make sense. So we are given 1 unit. That means we are given that 1 is a unit. That's all. Okay.
Sir,
Right,
I have a doubt.
Yeah.
Sir, we had said that we can divide a line into any n parts,
Yeah.
equal parts. So, sir, how can we divide it into 3 parts or something? I didn't understand.
Any part, says, suppose I have given a segment like this. You draw any line at an angle. Don't care any what angle and so on. Okay. Now take a compass. Take any distance in the compass. Keep on marking 1, 2, 3, 4, 5 like this. We have marked like that. Okay.
Yes.
Once I have marked, take this end point and take this last point. Join those two. Okay. Then through this point to this line, I can draw a parallel. That is
Yes,
only the ruler. This is again to draw a parallel, draw a parallel, draw a parallel. And since these are equal by construction, these also will be equal by construction, right?
Okay,
Because
sir, got it now.
similar,
Yes, sir, got it.
I can divide anything into any number of parts.
Okay, sir, got it.
Yes.
So, but to construct a parallel, like you can't just construct like that, right? Even for parallel line construction, there, like you have to construct the parallel line.
No, I can construct a parallel, right? And already I have shown you how to construct a parallel. Suppose I have a line like this, and I have a point outside like this. If
Yeah.
I construct a parallel, I just draw this perpendicular. That is known. And draw the perpendicular again like this. These two are parallel.
Yeah, okay. So, I was just saying you have to construct even for, you can't just draw like that. Yeah, I got it.
You can draw using perpendiculars, right? See, note that in the game we are playing today, so I can only draw right angles. Okay, and I can only bisect angles. Okay, and I can only replicate a length. For instance, if I want to construct a segment of length 4, so I can construct what I am given unit length. So I can just take a compass like this and then mark one more point like this, one more point like this, one more point like this. Okay, and if I want half a line, meaning half distance, so take one line, unit one length, and bisect that one. This will be half. This will be half. If you want 1/4, bisect again, it will be 1/4. If you want 1/5, use that other procedure to divide by 5 equal parts, like that. So you can always do that, right? So I can construct 1 by n. You can construct m by n, right? Because if I can construct 1 by n, I can replicate it m times. So m by n can be done. I also construct sorry, root a. So what are all the things we can construct using all these things? So basically, what are the things which you can construct? No, I can construct any angle. That is, sorry, I can construct any length. I can construct any integer length. M is an integer. I can construct that length. Can I construct m by n? I can construct that. So that means I can construct any rational number. Okay. And I can construct root of m. I can construct root of n. All those things I can construct. So I can construct m plus some k times root n. I can construct that. Correct? This can be constructed because I can construct m, I can construct root n, I can construct k, and k is an integer means I can construct all these things. Okay. Now, can we construct, let us say, can I construct, suppose I can construct, let us, A can be constructed, B can be constructed. Can I construct A into B and A by B? Let us investigate.
A is an integer.
Sir, repeated
A is not
addition of
necessarily
A,
an
B
integer.
times.
A is not necessarily an integer. In fact, can you construct root 2 into B or A by root 2? Can you do that?
So we can repeatedly add root 2 B times.
Huh?
So we
But
can
what if B is
repeatedly
not an
add
integer?
root 2 B times.
What if B is not an
Yeah,
integer?
can we construct? So root 2 I can do, B I can do. So root 2 plus B I can do. Yeah?
Yes.
Sorry, excuse me. B is not an integer. So B need not be an integer. So let me look at whether it can construct that one. Let me show you whether all these things are possible. So if I can construct A, if I can construct B, A plus B is obvious. I just mark like this one. And A minus B is also obvious. I have this A length, and then instead of marking B on the other side, mark B on this side. So A minus B can be done. And for A by B, let us follow this one. So you just construct this triangle. Please mute. Thank you. So I construct this triangle 1 and B, any angle, doesn't matter at all. Okay. And then extend this line and mark off A here. And then extend this line and draw a parallel to this guy. Okay. Now I have this triangle ADE parallel to ABC. So my AE by AC equal to AD by AB. My AE is B. My AC is A. Am I making a mistake? No, sorry, I made a mistake. One second. Let me get back again. So one second. Just a mistake.
Sir, AE is A. No,
Yeah.
AB is A, sir.
Yeah, the AB must be A. So I should have AB is equal to A and AE is equal to B, and this length is 1. Now again, so let's use that. My AC by AE is equal to AB by AD. By construction by AB is A. My AD is 1. My AC is what I want, X, and AE is B. That means my X is equal to A into B. So I construct, whenever I can construct A, whenever I can construct B, I can construct A into B. That means I can construct root 2 into even root 3 or root 2 into root 2021. I can construct all these things because root 2 is constructible, root 2021 is constructible, so the product is constructible. Similarly, if I just change it just one bit, take AB as A and AC as B, and I would have AE would be A by B. AE would be A by B. So I can construct A by B also, right? So from 1, you are given 1, I can construct all the rational numbers that we already have seen. All rational numbers have been done. And then I can construct the root of all rational numbers. All rational numbers. And then I can construct product of any of these two, any two construction numbers, and quotient of any two construction numbers. All these things can be constructed.
Sir, can we construct the product also by power of a point in a circle? So like the tangent will be the root of the product.
Tangent will be the root of, no, you have a circle here. So what do you do?
So if we take a point P outside the circle on that line, and then we draw the tangent, then and the intersection points with of that line with the circle are A and B, then PA into PB will be the tangent squared. Like that.
Yeah, we can do that anyway. So if this is A and then this is PA into, oh, okay, you can still do it. That's actually what you do is that if you put this as A and this as 1, so draw a circle on this as a diameter and then draw this tangent, and then this will be, this tangent length will be root A. That's okay.
Yes, sir.
Yeah, that's
okay. Sir.
This is 1 minus, this will be A minus 1. A minus 1 and 1 and then root A. Yeah, you can do that. It's not that that's the only construction. There's several others also. Okay. Right? So what are the things we can construct? I can construct addition, subtraction, multiplication, division, and square roots. So these are the 5 things we can construct. So let's look at D, the set of all constructible numbers. All constructible numbers. This has the property that meaning any two sum is there and then product is there, product division is there, and of course 1 is there and all those things. So this satisfies all the plus, minus, star, and division. So this is almost like our real numbers or the complex numbers or the quotient, rational numbers and so on. But it is much bigger than that because Q is inside this. Okay. And of course, definitely not equal to, because root 2 is not in Q, but it is in D. And we do not know how big is this. We don't know how big is it? We don't even know whether, okay, before that I have to explain one more thing, right? So what we have, what we can, suppose I can construct, let us say, cos 20 degrees. If I can construct cos 20 degrees, then I would be able to construct 20 degrees, correct? Because if I can construct cos 20 degrees means what? If I take this as, if this as length as 1, and if I just construct this 20 degrees means this length. So this, once I can construct this 20 degrees, I can always construct cos 20 degrees and vice versa. So if I have cos 20 degrees is in D, that would mean 60 degrees can be trisected. Correct?
Yes.
60 degrees can be trisected. That's what is possible. So suppose I can construct, suppose when will a regular polygon is 7 sides be constructible? I have a regular polygon like this. And suppose I can construct the 7 sides means what will be this length? Let me check what this length is. This angle is 2 pi by 7. Correct? Because it's a regular polygon 7 sides, central angle is 2 pi by 7. This is 1 and we say this is 1. And if I just drop this perpendicular, so this length, sorry, this angle, this angle will be what? Okay, 1. Sine, this is 1. So what will be this angle? This
So
is,
wouldn't it be 10, 90, and 80 angles?
we don't need that. Okay. So this is pi by 7. So this will be 90 minus pi by 7. This also will be 90 minus pi by 7. So what I
I'm
get
taking one in radii and one in degrees.
radii is 1. Radii is 1. And then this angle is 90 minus pi by 7. This also is 90 minus pi by 7. That means this length is 1 cos pi by 7. So 1 cos this one. That means 1 into cos 90 minus pi by 7. Correct? Because this is pi by 7. Okay, so that means the sine pi by 7. So this length is 2 sine pi by 7. So if I can construct 2 sine pi by 7, then definitely I could construct the regular polygon with 7 sides. I think there is a mistake somewhere. Let me check. 90 minus pi by 7. Yeah, that's okay. Not a problem. Yeah, so that's not a problem. So we can construct, that's what it would mean. So somehow, if we can show that when will cube root of 2, when will cube root of 2 will be, cube root of 2 will be constructible, whether if it is in the D, then I could double the cube. Correct? That also will be possible. That means I could double the cube. Somehow if I can construct that one, right? So for what we want to do is that we want to find out some characterization of which numbers are in D and which numbers are not in D. Okay. So that if we can do, then we are done. Right now. So as we saw, till March 29, 1796. So these are the only polygons which have been known to be constructible. Okay. Right. So now we saw all this in 3, 4, 5, and 6, everything we saw. 15 we didn't see, but actually there is a construction from 3 and 5. We can construct 15 also. So once I can construct 15, 30, etc., everything is fine. Or even 15 means what? 15 sides polygon means what should happen? 15 sides polygon is 360 by 15. That would mean 24 degrees must be constructible. So let me show you 24 degrees is constructible. Okay. Now let me show you 24 degrees constructible. So 15 also will be constructible. So what you do is that you just take, first of all, you will take, we'll show that 70 degrees is constructible. Okay. Suppose this is 36, this is 72, and this is 72. And then drop this one so that this is 36. Again, my OCB and then ABC are similar. So you can, this will be X means this also will be X. Okay, so this X is root 5 minus 1 by 2. So 36 degrees will be constructible. Since 36 is constructible, 60 is also constructible. So the difference is also constructible. So 24 degrees is constructible. So I can construct 15 degrees. Okay, so 15-sided polygon can be constructed. So let's not dwell too much into that. Okay, so these are the only polygons that could be constructed. Okay, so mainly.
So I didn't understand how you got 15 from 3 and 5.
Right, so let me show you again. Right. So I draw a triangle, isosceles triangle, with 36 degrees here, and then 72 degrees here and 72 degrees here. Draw in sense, consider that one. I have not drawn that, I consider that one. Then bisect this angle. This is 36, this is 36. Let this length be x. Okay, and let this length be x, and then this length also will be x. This length will be x. This is 1 minus x because this I have taken as 1. This also will be 1. Okay. Now, these two triangles are similar. So, this Y is this, A is this, and P is this. Mute, please. See, am I moved on? I'm on mute. Okay. So if I do this one, so my triangle OCB and then OAB are similar. So I'm going to write down the proportionality conditions here. So this x is opposite to 36 in this triangle. What will be opposite to 36 in the other triangle? So this is x. So what is opposite to triangle in this triangle? In this triangle is 1 minus x. So x by 1 minus x. And this is opposite to this 72 here, this angle here, which will be opposite to the same thing here. It will be x again here. Okay, because that's opposite to this guy. Okay, that will be 1. That means our x by 1 minus x is 1 by x. So if I just multiply it out, I get x square plus x minus 1 is equal to 0. So x is root 5 minus 1 by 2. Now we know root 5 is constructible. We know 1 is constructible. I can divide any line. So this length is constructible. This length is constructible. So I construct that length and draw an arc of a unit radius circle at both the end points. Then that point will be this will be equal to 36 degrees. So I have constructed 36 degrees. Since I can construct 60 degrees anyway, so this, if I just construct a 60 degrees at this end point, the remaining thing will be 24 degrees. So if I can construct 24 degrees, that will mean that the 360 by 24, which will be, okay, 360 by 15 is equal to 24 degrees. That I could have constructed a central angle for the 15 degrees polygon, sorry, 15 sides polygon. So that's where I constructed 15 sides polygon. So that's why I said 15 is possible. Okay. But there's one more construction also, which is slightly long, but we don't have to go into that. This is quicker, meaning by computing the this side for which one angle is 36 degrees, other two sides are 1. Okay. Now this is the known knowledge from till that time. From when? From 2 to 3 century BC. For 2000 years, only this was known. Okay. Then something remarkable happened on March 29th. A young CF Gauss, called Friedrich Gauss, who is a German mathematician, at the age of 18, right? He created a straight and compass construction for regular 17 gun. Okay. And note that this problem was open for 2000 years, and a young person with just 18 years of age finds solution to that. And initially, he was supposed to study linguistics, meaning he was supposed to master the languages in the university. And after this spectacular achievement, he decided that he will devote his entire life to mathematics. This is one of the most prolific and then deepest mathematicians of our times, probably after Newton. And he announced this result on April 30. That means he was at the age of 19 at that point in time. Which was also published sometime later in 1801. There are lots of things which are attributed to his name. So there is something called the Gaussian curvature. This comes in calculus. There is something called the quadratic reciprocity law. Okay, and this comes in number theory, and so many things. In fact, Gauss was of course, yeah. He also contributed a lot of things to physics, and Gauss was a child prodigy. In fact, when he was 3 years old, he pointed out the error in the computations his father was making in the tax computations. And also, most of you would have heard about the story which Gauss, as a young first-standard student, found out how to find the sum of the numbers up to 1 to 100. See, these small children, no, they usually they'll be noisy in the class. So what the teacher used to do is that give a sum like this, meaning sum up to 1 to 100, and then you can rest for about 15-20 minutes when they are doing this sum. But as soon as the sum was proposed, and then Gauss immediately wrote the answer as 50-50. And because he did a smart thing, like you just reverse this and add, we have 101 times 100 times 101, that is 2 times s, which is equal to, so s is equal to 50-50. Basically what he discovered was 1 up to n is equal to n into n plus 1 by 2. Okay, so he was was such a great mathematician, and tomorrow we will see how he accomplished this remarkable feat of finding that yes, a regular 17 gun is constructible. And of course, we will construct it also. He was so much pleased with this, and he said, there's a monument, there's a statue for him in Germany, and the pedestal is in the form of a regular 17 gun. Of course, the regular 17 gun will not be distinguishable from a circle in any way, because suppose if I just draw this regular 17 gun, let me draw one and then show you. It won't be distinguishable from circle at all. Okay, let me show that. It's very, get rid of this one and this one also. Suppose let me show you how it is. Then suppose I have a even like this, and then if I draw a regular 17 gun here, so it almost looks like a circle, correct? I mean, there's no difference between a circle and this one. If you really draw the circle also through this one, hardly distinguishable, right, between these two. So what they did was, instead of course, the pedestal is in this form. It's in the form of a circle. But is doing that, since it could be distinguishable, what they did was they just joined all these lines like a 17-pointed star. So that was what is given there. So they would you would see that on the top of that pedestal, you will also see a star like this, which is a 17-point star and so on. Okay, so that was this achievement. And then what he did was he computed this one, cos 2 pi by 7 to be this quantity. He computed at 16 cos 2 pi by 7 is minus 1 plus root 17 plus root of 34 minus root 2 root 17 and all those things. Now we already know that root 17 is constructible. So this is constructible. This is constructible. So square root of that also is constructible. So this is constructible. This is constructible. So this root is constructible. Product of two things is constructible. This also is constructible. The whole thing is constructible. The root is also constructible. So this point, this length is constructible. That's what he proved. Okay. Not only that, he proved for which values of n, for which when a regular polygon of n sides can be constructed. That's what he showed also. So gave a simple formula for that. So the formula is also, okay, we will state the formula later on. So this was his achievement among others. This was probably his first achievement in mathematics. Okay, right. So that's what we are going to do in today's class and the tomorrow's class together. Okay, right. Let's go back to finding. So what is our criteria? What is our aim? D is the set of all constructible numbers. Constructible numbers. Okay, and we want to find a criteria to decide whether a given real number, given number A is either in D or A not in D. We should be able to decide by looking at that number itself or by making some simple checks whether this will be in D or this will not be in D. So that's what we wanted to check. So once we can do that, then we can solve many of these problems. In fact, we can solve that a 7 polygon is not constructible, and 9 is not constructible, 11 is not constructible, 13 is not constructible, like that. So we can always do those things. We'll also show that 60 degrees is not trisectable. Okay, and we'll show that cube root of 2 is not in D. That means doubling a cube is not possible at all. Okay, so all those things we will show if we do this. If I can find a nice criteria to decide whether the number is either in D or not in D. So that's what our aim is in today's class.
Sir, if this 7-sided and 9-sided is not possible, then how did Gauss construct 17-sided?
17 is possible. 17 is possible. 7 is not possible.
Sir, also, how do computers construct the polygons? Because we cannot construct all the polygons. So how are computers doing it?
That's a different story totally. Okay, so they don't construct exactly. They don't use ruler and compass, right? They don't have to use ruler and compass, right? Do they have to? No, because I can construct seven polygon of 7 sides. What I will do is that I will just do this 180 degrees, and I will divide this into 180 by 7. I can construct. I can 360 by 7. I can compute this to any approximation, and then measure that angle and then construct that, right? So, and again, in a computer screen, you will never know whether it is exact or not exact at all. So the angle, say, beyond a certain stage, we can't even do that. For instance, if I just instead of this one, suppose let me delete this guy, and then I just the same thing I will construct 7th degree polygon. Sorry, polygon of 7 sides. So I can do this one. It does that, right? But the point is that, see, this is not exactly this will not be exactly the angle which you want. So if you just look at the center of that, it will be one of those. 1 minute. If I just join this. Oh, sorry. Oops. Undo. Yes. If I join this and join this, and then measure this angle. Okay, it says it is 51.43. Okay, this 51.43, how close it is to, let us say, 360 by 7. So 360 by 7 is still, it is 51.43, but because the approximations are the same, so rounding is, suppose if I just even 15 decimal places, right? So you already look at this one. One of them is 51 point, etc. 144, but this is 143, right? So already there is a small rounding up. If I just, okay, 15, beyond 15, I can't do that. This 144, there's a difference in here itself. So it will not be exact. It will not be an exact. If you have a very fine instrument to measure the sides, there will be a small difference. But we cannot judge the difference at all by looking at the figure. So that's how they draw. So the computers are probably, I think, telling a lie to us, okay, in all these things. But we will show conclusively that D does not contain that cosine of 2 pi by 7. So cosine of 2 pi by 7 is not in D. And similarly, we will show that 60 degrees cannot be trisected using straight edge and compass. Okay. In fact, there are lots of people who do not believe this kind of can't be done thing. Okay. So actually, when a couple of years ago, I met a teacher who is teaching in a reputed school, and then he came to me and said that all these angles cannot be trisected is all uh, not true, and I have a construction which will trisect any angle. Okay, and he showed me the construction. It was very, very complicated. And he showed me that it is basically constructing and so on, meaning it's trisecting and so on. And then I asked him to read the proof and then see where is the mistake. Okay, so if he is right, the proof of this one must have a mistake, right? So he asked him to go back and then read the proof that an angle cannot be trisected, and come back to me and say that where the mistake is. And he hasn't come back yet. Okay. So anyway, that means that you would have been convinced. So this angle trisection is when mathematics says that something cannot be done, it cannot be done. Period. It's not that it cannot be done by me or you or anybody else. It can't be done by anybody else. Meaning it can't be done by mathematics at all. That's what it means. Okay. So let's go. Okay, that what. So our aim is this is what we have to do. We are going to find out a criteria for to decide whether a number is constructible or not constructible. So once we do that, then all the things will fall into place automatically. Now, we already said that, suppose, let us start with the set of all rationals. This is set of all rationals. Okay, now, from this one, we already know that any rational and another rational and another rational, these numbers are all constructible, right? These are all constructible. How many steps I need to do this? That is, see, what are the things I can do? I already know that. Suppose I am given 2 points. Suppose, for instance, let us use for some clarity. Let us use a plane with an x-axis and a y-axis. Take a point A, B. If A and B are both constructible, let us call this point as constructible. Okay. So suppose if I take a point AB is constructible, and then another point CD is constructible, I can draw a line like this, right? Using a rule, using a straight edge. Similarly, I can do like this also. So how can I, suppose given all these constructible numbers, suppose I have this constructible numbers like this from Q, I have constructed all these numbers, A plus B into root of C, where A, B, C are in Q. This is all we have done so far, okay? Now, using this one, can we construct any new numbers? Let's say, this is AB is a constructible point, this is a constructible point. If I draw a line like this, draw another line like this, I can intersect this point, isn't it? Will this be a new point, which is not in this form? Can I get a new point like this and it's not in this form? Suppose I start with rational numbers, let us say. Suppose I start with just rational numbers alone.
Sir, no, right? Because we'll get a linear equation for that straight line, so it can't have cube roots or anything in it.
So I have a PQ is a rational, RS is a rational. Similarly, I have P1, Q1 is a rational number, and R1, S1 is another rational number. Then the intersection point also will be rational only, right? Rational and rational. So my intersecting two straight lines, this does not give me a new number. Does not give a new number. What about circle? Suppose I have a circle through a known point and a known radius r. So this is constructible, and this is also r is also constructible. So A and B are constructible, and r is also, all of them are rational, let us say. Okay. Now I have a line also like this, which is a constructible number. So it will be of the form, let's say Px plus Qy plus some else equal to 0. What about these two numbers, these 2 points? What will be the form of that one? So this equation is x minus a whole square
X minus a whole square plus y minus b whole square is r
equal to
square.
r square. I'm going to find what is x from these two. That's x coordinate of this point and this point. So what I will do, I will find x in terms of y, which will be px is equal to, or y in terms of x, qy is equal to minus px minus l. So y is equal to minus px minus l by q. So if I
Sir,
substitute,
so we'll get a quadratic equation only, right? So
yeah.
it can't have.
So I have x square plus y square minus 2ax minus 2by plus a square plus b square minus r square is equal to 0. We substitute it here, what will I get? X square plus px minus L by Q whole square minus 2a into minus px plus L by Q, oh, sorry, 2b into minus 2ax plus equal to 0. So if I expand this, what will I get? I will get something like a times x square plus b times x plus c times 0. What are a, b, c? They are all rationals. So my x will be minus b plus minus root of b square minus 4ac by 2a. That means I can only use, that is if I write it as minus b by 2a plus 1 by 2a root of this one, I can only get point of this type. So by using the procedure of either intersecting straight lines or circles, let us call that as one step. That is, one step says that one step process, either I intersect two straight lines or we intersect two circles or intersect one circle with one straight line. So intersecting two circles is same as intersecting a circle and a line, because if I intersect two circles means it's same as intersecting this circle and this line. Okay, that's the same thing anyway. That means I have like this. Okay, so by using one step process, that is, if I start with Q by using one step construction, let us call that as one step construction, which would mean that either intersecting two lines or two circles or one circle and a line, we can only get this set, that is a plus b root c, where a, b, c are in Q. Let us call this as, let us make a point like this is f naught, so that we can easily compute. This will be f1. Okay, so f1 is got from f naught. Okay, f1 is got from f naught, such that with a one-step construction means I could have constructed only these numbers. What will happen if I construct the same thing to f1? What will be the things I will construct f2? F2 will be of the form a1 plus b1 into root c1, where a1, b1, c1 are all in f1. Correct? Because the same thing happens. So here, if I take any of these forms, suppose something is a1 here, b1 here, and c1 here. So what will happen is the same thing. Here we have not used anything like rational numbers and so on. We just used a equation like this, which is valid for any number. Okay, that means if I can just use the same thing, I would have got f2. What is happening? Yes, one.
Sir, with the current knowledge, we can also calculate any even root, right?
Even?
Root.
Yeah, we can do that, but let us do one step at a time. That means I have, for instance, I have my root 2 is in f1. That means root of root 2 is in f2. That means 2 power 1 by 4 is in f2, correct? So similarly, I can, so that see, we don't want to go, meaning combine steps like this. We don't want to do that at all. So this is not our aim now. Okay, what is our aim is that what happens if I construct methodically one step at a time. That is, if I take one step at a time. That is, if I start with rational numbers, a plus b root c, and this one. Okay, you may wonder that what about is this closed under plus, minus, star, and division? Plus is obvious because a1 plus b1 root c1, sorry, a1 plus b1 plus root c plus a2 plus b2 root c is equal to a1 plus a2 plus b1 plus b2 into root c, correct? right? So that's what it was. So similarly, this is under addition, it is fine. Subtraction also it is fine. You can easily check that a plus b root c into c plus or a plus b, a dash plus b dash root c. It's also the same form. You can easily do that. And 1 by a plus b root c, I can calculate as a minus b root c by a square minus bc square. And this will not be 0 because c will not be a square, so b square c. So this will not be
B
0.
square.
So this is okay. This is fine. So what we have done is that suppose I have my q. If I add a root c, then this is what I get: a plus b root c, where a, b are in q. I can add one more root c. I can add one more root, let us say d. Then I will get the same thing. That is, suppose this is my f1. As I said, it could be like this: a1 plus b1 into root d, where a1 and b1 are in f1. So at each point in time, I will add only one square root, either one a1 or one a2, like this. So that way I can keep on building. That means I can, starting with f naught, which is equal to q, I can build like this one. It will be q of root, say, a1 or root k1, which I will write it as f1. And from this, I will write it as f1 adjoined to root of k2, where k2 is in f1. This I will write it as f2, and so on. I can keep on doing that one. Okay. Now, these numbers are constructible from q. We already know that. So these numbers are constructible from f1. So these are also constructible from q also by 2 steps. Okay. So what I can do is that if to construct a number in this one, I can construct a it will be as an intersection of two circles or a circle and a line in f1, and any of those things are intersection of two circles or lines in the q itself. So if I start with q, anything in this step, anything here could be done in one step. The next one is anything can be done in 2 steps. Anything can be done in 3 steps and so on. So if I can construct a point in n steps, it will be at the nth stage in this cycle, in this in this chain. Yes, Parth.
Sir, Q is the set of rational numbers, right? Then how are we treating it as a function also, like Q of root C?
No, I'm not taking it a function. I'm just using a notation. That's all. Notation is my
Okay, sir.
q root c would mean by definition. I will put q root c means the set of this set. That's all. It's just a definition. I'm not saying it is a function or anything like this. I'm not saying anything.
Okay,
All the functions and all those things I do not know anything at all, so I don't care. Okay. Yes.
Okay, sir.
Joshua.
No, sir, by mistake.
Smithali.
Sir, I think I will run the method. Sir, for my last time that
your voice is breaking.
A cube plus B cube equal to 60 or A raised to
No, your voice is breaking. Your voice is breaking, Smithali. Can you put it in the chat? Hello. Okay, I think she has. Okay, if you find your mic correctly, then you can just come back again. So what we have shown so far is that, so if you can construct something in n steps, okay, if you can construct something in, oops, what happened?
Sir, am I audible?
Yeah, please.
Yes, sir, I wanted to tell that we can also do this using Fermat's last theorem. Because what do we do for constructing any, say, under root A kind of thing? We use Pythagoras theorem or something similar. But for a greater order of sort, Fermat's theorem says that the A raised to n plus B raised to n equal to C raised to n has no solutions greater than or equal n greater than 2. So can we use that?
No, I'm not sure. See, Pythagoras theorem is a square plus. Oops, I think there is a mistake here. Let me 1 minute. There's a problem with this. So let me come back again. Oops. Where were we? Yes, here. See, Fermi, I'm not sure what you are saying. A square plus b square is equal to c square is Pythagoras theorem. And then a power n plus b power n is equal to c power n. That is, this has no solutions. Is if I understand, that is the Fermat's last theorem, right?
Yes, sir. So, sir, can we use this fact because only for we have source only of order 2 where we can we can do some
No,
constructions.
I don't think they
So,
are related. I don't think they are related, and I'm not sure such a deep result is involved in this at all. Okay,
okay, sir.
it's pretty deep, and then I don't think we need. See, what this says is that the sum of two nth powers of integers is not the nth power of an integer, right? Here we are not
Yes, sir.
interested. Here we are not interested in that. A and B for us can be rational numbers. Can be. They can even be numbers like square root of 2, right? Or square root of 1796, like this. Even this one. So these things do not have a place in this kind of stuff, right? So I don't think this is connected in any case. But anyway, let's path.
So does q of root of c mean the same thing as f1?
Yes, q of root of f1 is the same thing. I'm just naming them. That's all. I'm giving a name. That's all. See, q, which is if I add root 2 to this, add in this sense, meaning add, the correct sense of the word. That is, what I consider is all the numbers of the form a plus b root 2, where a and b are rationals. This is the construction. This is the one-step construction.
Sir, also, can you please repeat the part where how we reach from f0 to f1? Like, what is the process of interchanging, or is it just any ambiguous variable and we name it as
No.
fn?
F0. Okay, let us take q for instance. I want to find what happens if I can construct in one step. Let us say by adding a root 2. By adding a root 2 means whatever can be constructed by adding one in one step is a number of the form a plus b root c only. That's what I'm claiming, because if I take two rational points, that is a, b, and c, d, the line between them has rational coefficients. So if I just draw two lines and I can't take this intersection point is not a new point at all. It's again a rational point. So if I have to extend this q to more constructible points, I have to always use a circle. A circle with a line, we already saw that this circle has rational coefficients. That is, it's of the form x square plus y square plus 2gx plus 2fy plus c is equal to 0. This line also has rational coefficients, lx plus my plus n is equal to 0. The intersection point is not necessarily rational, because these 2 points will be of the form a rational number plus another rational number into a rational number root of that rational. That's how this will be, isn't it? So that means from Q, I can get all numbers of this type only by using one step. That's what you're saying. Okay, that is my F1. So my F0, I define it as Q. I'm just giving a name, like whatever name we give to children. This is our first child. This is Q. The second child, which is got from F0, is named as F1. What will be F1? It is got from Q by adding a square root. And my F2 will be the third child. Let us say it will be got from F1 by adding another root for which an element in this one, for instance. So let's take some examples so it will be very clear here. Let's take this, for instance, right? So let's take this example. Well, this will be constructible or not? See, I know that root 3 is constructible. So where will this be? This will be in, let us find out where this will be. This will be in Q, and first I add root 3, correct? Okay, then I will add root 3. Then I can add root 2. Root 2 is not in this one, so I will add root 2. So I will add a root 2 to this one. Then 1 I don't add because root 2 will contain that one. So I will add a 1 plus root 2 here. So 1 plus root 2. So if this will be there. This is there, this is there, and this is there. So I will add a root of that also. That is 1 plus root 2, root of that, plus root 3, plus root of that one. I can add this root. Then 5 is already there, no issue at all. And I can add a root of that also. Then root 6 is need not be added at all because my root 2 is there, root 3 is there, the product is there, root 6 is there, already there. So this will be got by how many steps? This is the first step. This is the second step. This is the third step. That root is the fourth step. This root is the fifth step. So it will be got in 5 steps. Okay. So that's what I said. So we have in the fifth step, I would have got this.
So why do you add that root 2? You added root 3, then root 2, then 1 plus root 2. Why can't you just add 1 plus root 2?
Why can't we add 1 plus, see, root 2 cannot be directly done, right? First of all, I have to add root 2 because root 2 is not in Q. It is not in Q. First of all, I have to say root 2 has to be added. Then 1 plus root 2 will be in Q1. 1 plus root 2 will be in F1. So I can add 1 plus root 2 square root. So that's why I say F naught is 1 root 2. Then I can add 1 plus root 2. This is not in F naught. So this will be root of that will be in F1. Similarly, I can add root 3 because root 3 will not be in this guy. Then I will add root of that because 1 plus root is already there in F1. Sorry, F2. So F3 also will contain the same thing. So this will be in F3, the root of that one. Then I add one more thing also, one more square root for that. Root 6 I don't add because root 6 is already there in this chat. Because I have added root 2 here. F1 will contain root 2 and F2 will again contain root 2. And if I add root 3, root 6 will be in F3 itself. Root 6 will be in F3 itself. So I don't add that specifically at all. Okay. So this number is constructible. And how can I construct that? By following steps like this one. So we have a nice criteria for constructibility. What is the criteria? So I can construct, okay, I can construct a number only if, okay, you can even say if and only if and only if we can find, let us call this as a tower, okay, like this. My first is F naught, which is equal to Q, and then my F1 is same as Q time Q added to some K1, let us say, and then my F2 is F1 added to some K2 and so on. Okay, so I can just keep on doing that. And suppose if I say my Fn is Fn minus 1 added to root of Kn and my number A must be here. For some n, okay, it can be 10,000 or 15,000, I don't care. For some value of n, A must be possible to extract, must be able to be constructible in this form. Then only it is constructible. Okay. So suppose we can prove that my cube root of 2 is not in Fn for any choice of n and for any choice of k1, k2, kn, then we are done. Then we would have proved that my cube root of 2 is not constructible. So yes, cube cannot be doubled, right? So let me state this. So the criteria for constructibility right, is that so a number A is constructible if and only if there is an n, there is a positive integer n and constructible and numbers k1, k2, etc. up to kn such that q equal to f naught and then contained in f1, which is same as q added to k1, contained in f2, which is same as f1 added to k2, and so on up to fn, which is same as fn minus 1 added to kn, and my a will be in this fn. only then. So whenever I want to show something is constructible, I have to show this sequence. Okay. For instance, what Gauss did was exactly that. Gauss did that it is possible to build this 16 2 pi by root 17 in a sequence of steps like this, adding root 17, adding this, and adding this, and adding that. Lots. That's what it did. Okay. Yes, Ritvik.
So what is K again? Can you repeat?
These Ks are in the previous ones. That is, first of all, K1 will be a rational number.
Yeah.
K1 will be a rational number. K2 will be in F1 and so on. My K, okay, I can even add this. Ki will be in K minus, sorry, Fi minus 1. Ki will be in Fi minus 1. My K1 must be a number in F0. K2 must be a sorry, number in F1. K3 will be in F2 and so on. That's what we did.
Yes, sir.
Yeah, so that's also Ki must be in Fi minus 1. So if I can find a sequence of numbers like this, then it is constructible. If I can't find a sequence of numbers like this, it is not constructible. So that is the criteria which we have derived today, and we will use it tomorrow to construct, okay, to prove or disprove something is constructible or not constructible. Okay. Okay. I think we are run out of time. So any questions? Okay.
Yes,
So
sir.
yeah, think about that. Think about these things, what we did today, and we will see tomorrow. Tomorrow, yeah, we will see tomorrow and then complete this proof. Okay.
Thank you.
Thank you, sir. Bye, sir.
Bye.
Thank you, sir.
Okay, thank you, sir.
Hi, sir. Thank you.
Thank you, sir.
Thank you,
Bye.
sir.
Sir.
Sir.